Okay, welcome everybody for our weekly meeting at the Department of Marine Geosciences weekly seminar series. And today we're hosting Dr. Charlotte Rahlves from the University of Bergen in Norway. So thank you very much for coming, Charlotte. Charlotte, a little bit about Charlotte. Charlotte Rahlves is a PhD fellow in ice sheet modeling at the Norwegian Research Center, or NORCE, and the University of Bergen in Norway. With a background in meteorology and geography, she investigates the future evolution of the Greenland ice sheet and its impact on global sea level rise, using advanced numerical modeling techniques. Beyond glaciology, Charlotte has worked on boundary layer meteorology and large eddy simulation for wind energy. She is also dedicated to science communication and transdisciplinary communication, emphasizing the societal and ethical dimensions of research. So thank you, Charlotte, again. And today we're going to hear her talk about from ice to impact, the critical role of ice sheets in global climate change. Thank you, Charlotte, and for the video.
Okay. Thank you, Nicolas, for the invitation and for the introduction. I have to do one small correction. I'm not yet a doctor. I'm working on it. I'm still working on this, and I am expecting to get the title within this year. So yeah. But yeah, so you already said that I have a background in meteorology. I've been living in Bergen in Norway for the past 3.5 years, and I'm a PhD candidate at the Norwegian Research Center, where I investigate the future evolution of the Greenland ice sheet. And I do this mainly by using numerical modeling techniques. And Nicolas was kind enough to host me last December when I visited the University of Haifa, which was a very nice experience. I think you have a very impressive and unique campus. And so I'm glad that today I can contribute a little bit to this. All right, so I'm going to be talking about ice sheets today, and it might seem a little bit far away from where you are, but I'm sure that I can show you the connection that ice sheets have even to you in the Middle East. Okay. So what are ice sheets? Ice sheets are continental scale masses of ice that cover vast land areas. So the difference to glaciers are that we have glaciers in mountainous regions all over the world, but ice sheets actually really extend over the entire land mass, sometimes of a whole continent. And the name already suggests something. So ice sheet means that the aspect ratio is really in a sense that if you take, for example, 3 sheets of regular A4 paper and put them together, then this is the same aspect ratio that an ice sheet has. So ice sheets are much larger in extent than they are thick. So we have these 2 ice sheets on our present day Earth. We have the Antarctic ice sheet and the Greenlandic ice sheet. And a little bit of facts about these 2. The Antarctic ice sheet covers the entire Antarctic continent. It holds a potential sea level rise of 60 meters. So if all the ice was melted on Antarctica, we would experience a sea level rise globally about 60 meters. And an Antarctic ice sheet also holds about 90% of the fresh water that we have on this planet. So I am focused mainly on the Greenland ice sheet. That's a little bit of a smaller ice sheet, but still has a sea level potential of 7 meters. And I'll show you throughout my presentation why the current focus is very much on Greenland at this moment in time. So the Greenlandic ice sheet covers around 80% of the Greenland surface. And I always like to remind everyone that it's not just, so what we are researching is not just masses of ice, but there's also actually people living in Greenland. Greenland has about 60,000 inhabitants. Greenland is in its native language called Kalalit Nuat, and it has a capital with 19,000 inhabitants, which is Nuuk, and it is the world's smallest capital. All right, so how do ice sheets work? Ice sheets grow over thousands of years, and their mass balance is determined by surface processes and ice dynamics. So we have the gain of mass, which is the accumulation, and that is mainly due to snowfall in the higher altitudes. And then mass can be lost through various processes. So for example, surface melt when the ice reaches a little bit lower surfaces or lower altitudes where we have higher temperatures. And then this melt can run off the surface of the ice sheet. And then this mass is lost. We also have mass loss via sublimation or basal melt. So basal melt happens due to the geothermal heat flux. We have subglacial melt. That is when the ice sheet flows over the edge of the land and gets in touch with the ocean, and everything that happens below the water or in the water below the ice sheet is subglacial melt. And then we have the breaking off of ice into the ocean, and that's called iceberg calving. So what happens is that snow accumulates over a long time, and it gradually compresses into a more dense version, which is called firn, and it compresses under its own weight and eventually turns into ice. And then it flows under its own weight from the interior of the ice sheet towards the margins. So that is correct. Ice can flow. Ice is actually a fluid. It just happens on very, very long time scales. And here you see a satellite image where the regions of high flow are highlighted in red. So we see that there's a lot of high flow regions towards the margin of the ice sheet. And the flow speed in the margins can reach up to several kilometers per year. Oops. So now I lost that. Okay, one thing that I find quite fascinating about ice sheets is that when you drill into an ice sheet, you can actually find a whole archive of past climates. So these ice cores that are being drilled in Antarctica and also in Greenland are windows into the past, because they hold these ice layers that accumulate over time, and they contain trapped gases that reflect the historical atmospheric composition. And through oxygen isotope analysis, we can actually determine past temperatures. So in Greenland, the oldest ice that we have found so far is about 130,000 years old. And in Antarctica, there has been ice found that is over 800,000 years old. And at the moment, there's actually ongoing effort. It's a project called Beyond Epica, and the aim is to find ice that is more than 1 million years old. And for me, this was actually the first time many, many years ago where I really understood how we know for sure that climate change is actually human-made, because in these ice cores, we see that today the CO2 concentration that we find today is really unprecedented in the past history of the Earth, or at least as far as we can go back with the ice cores. Okay, back to ice sheets and their interaction in the climate system. So ice sheets are an integral part of the climate system. They interact with all the other spheres, so with the atmosphere, with the ocean, with the biosphere, and with the solid Earth. So for example, through certain feedbacks with the land, through freshwater input, so all the ice that breaks off or melts into the ocean can alter ocean currents. It adds nutrients to the water around and therefore influences the biosphere. And it does interact with the solid Earth, for example, through isostatic rebound. And I'm going to go a little bit into some details here. So just one example of a feedback or of an interaction that is really important for the entire climate system is the albedo feedback that we have. So just real quick, albedo is the reflectivity of the surface. So snow and ice have a light surface and therefore they reflect sunlight much more readily than bare ocean water, which is rather dark and absorbs much more sunlight and therefore has a low albedo. And why that is important comes to show here when we speak about the Arctic amplification. So the Arctic warms much faster than the global average, about 2 to 4 times faster. And that is largely due to the seasonal sea ice and snow cover change that we see in the past decades. So the Arctic usually is covered during winter in sea ice, and this sea ice retreats during summer, but never really completely retreats. But in the past decade, we have seen summer sea ice retreat more strongly than ever before. So, and this leaves vast areas of dark ocean surface exposed, which can then absorb more sunlight and warm up much stronger than the area would under sea ice cover. And the same goes for retreating ice sheet margins. So as soon as land is exposed by retreating ice, we have a much higher warming due to the absorption of sunlight. Okay, interaction with the solid Earth happens mainly via isostatic rebound. I assume that that's probably something that you guys maybe know much more about than I do. It's pretty straightforward. The moment that, so the ice cover is a weight on the Earth's crust and it presses down. And as soon as ice melts or we lose ice sheet mass or ice retreats, this weight is lifted and the mantle of the Earth can adjust to this lifted weight and lifts up. A little bit like a memory foam mattress. This happens on very large time scales. And this is the reason why we actually observe around Greenland today a sea level lowering locally, and this is because of this effect, the land masses are moving upward. Okay, so the Greenland ice sheet can lose or gain mass through different processes. Again, main gain is precipitation, so in fact snowfall. We have runoff, so melt that runs off the ice sheet, and calving of icebergs. And I want to go a little bit into these processes. And a really important role are the marine terminating outlet glaciers around Greenland. So that's the part where the Greenland ice sheet is in contact with the ocean. And these glaciers act as a transporter of ice that flows from the interior of the ice sheet towards the margins and then into the ocean. So what happens there is that ice regularly breaks off, big chunks of ice break off and drift away as icebergs and eventually melt. And this process is called calving, which is a natural process. It occurs regularly. The key processes involved are stresses that lead to this breaking of icebergs, and submarine melt at the ice-ocean interface that can also increase iceberg calving by, for example, undercutting the ice. And this delivers a big source of freshwater input into the ocean, which can, in the end, affect ocean circulation and also alters the local ocean salinity because we add fresh water. Okay, so this is a schematic representation of such an outlet glacier. So we have different forcings that act on this outlet glacier. For example, we have warm ocean currents that can enter these small fjords in which these outlet glaciers exist. And then as soon as they reach the ice, into the ice phase, they can start melting ice. At the same time, because these glaciers, the outlet glaciers, are in very low altitudes, they also experience surface melt, and this surface melt can drain through the ice through crevasses and moulins, and it can then move at the base of the ice as subglacial discharge and be discharged at the ice ocean phase. And what happens is that this ice discharge, this subglacial discharge water is fresh, so it is buoyant and it will rise up at the ice phase, where it mixes with the surrounding water and creates this buoyant turbulent plume, which plays a really important role in the melting at this ice-ocean interface as well. And this then also can enhance ice calving and icebergs breaking off. Okay, so these processes, I have to say, are really complex and happen on very large, on a large range of scales, and they are therefore very, very hard to model in numerical models. And they're also not very well understood yet. So we really have only a basic understanding of the processes interacting here. And I want to show one example, which is the Samek-Kujalek glacier. It's also called Jakobshavn-Isbre. A lot of glaciers in Greenland have multiple names. Some are derived from colonial times. Some are going back to their indigenous names. So it leads to a lot of confusion sometimes in scientific literature. But so here I choose the indigenous name Samek-Kujalek, which is one of the biggest and fast-flowing glaciers in Greenland. And it has experienced a significant retreat since the 1990s. You can see here different lines of where the glacier front was located. And this alone, only this glacier is already responsible for around 4% of the 20th century global sea level rise. So we really understand here the importance of these outlet glaciers. And they serve in a way as key indicators of ice sheet response to climate change. And it's it's really interesting we want to understand how they might react in the future, because if they might lead to a destabilization and rapid drain of ice and ice sheet mass loss. Okay, I want to also talk a little bit about some feedback mechanisms. So I already said the ice sheet reacts or interacts with other components of the Earth system. And we have some self-reinforcing mechanisms, which are then called positive feedbacks. So these are processes that where the initial process is reinforced. And one of this, a really important process, is the surface mass balance height feedback. The surface mass balance is basically the mass gain and loss that happens at the surface. So in its most simplest form, you could say snowfall goes in and melt goes out. And this is basically the surface mass balance. And this is very much determined by the elevation on the ice sheet. So in higher elevations, we have lower temperatures, so we have a more positive surface mass balance. But if we see a decrease in ice sheet height, because maybe we have some initial melt and the ice sheet surface slowly decreases and comes into lower altitudes where we have higher temperatures, then we get an even more negative surface mass balance, and then even more melt and an even lower surface. And this is a self-reinforcing positive feedback. The same goes for the land albedo feedback. The more the ice sheet retreats, the more land is exposed, which means that we have warmer temperatures because this landmass reflects less of the sunlight and heats up the surrounding air much faster. A negative feedback would be something where an initial process is counteracted. So the isostatic rebound would be an example of this. The ice sheet loses mass, but then the mantle rebounds and lifts up the ice surface, which then comes into colder temperatures, and then the initial trend is counteracted. Okay, why is this so important? Why do we even care about ice sheets and how they, react to climate change? Why does it concern us? And the big answer is that they are very important for sea level rise. You see here a picture of me in the South Pacific. I was lucky enough 2 years ago to visit Fiji on a summer school trip. And so the South Pacific is really one of the areas in the world that is really highly affected by global sea level rise. Already now, there is villages in Fiji that had to be evacuated completely and relocated due to increased flooding in the past decade. And then there is the nation of Tuvalu, which has already decided to become a digital nation because it is only located at its highest point around 4.5 meters above sea level. And so it is very vulnerable to sea level rise. And it's kind of known that this island nation will most likely not survive in the future. So this is basically the motivation why we're doing this. And just to give you some background on currently observed sea level change. So sea level changes due to different contributors. The biggest contributor is the thermal expansion of the ocean, of course. Warmer waters take more volume. But then the other big contributors are water that is added from land glaciers and from ice sheets. And the Greenland ice sheet is becoming a more and more important contributor. And this has also to do with the Arctic amplification that I talked about a little bit earlier. And we see that the Arctic is warming so much faster and Greenland is losing mass at an accelerated pace. Okay, when it comes to sea level change, when we speak about global sea level change, this is not distributed uniformly. So sea level changes regionally differently, and this has to do with many factors, with ocean currents, with wind patterns, with land motion locally, with thermal expansion and gravity effects. So we see here on this nice little map that, for example, the Southern Ocean or the Pacific is much more affected. The Southern Pacific is much more affected by global sea level change than, for example, around Greenland, where you see the blue areas, which means that locally around Greenland, sea level is actually lowering. Okay, that's just important to keep in mind, because a lot of times we come up with global average numbers, but they mean very different things for different regions of the world. Okay, so the main point for us as ice sheet modelers is we want to project the future of ice sheets. So we want to know, how do they respond to climate change? How much contribution to sea level rise can we expect from them? And then if we look further into the future, we also want to know, under which conditions can we expect a stabilization of Greenland in the future? And we do this mainly with ice sheet modeling. And ice sheet modeling, in a nutshell, basically means we take a domain, which is here Greenland. We discretize the domain in space and time. So we put a grid over it, and we solve physical equations at each point, whereby we can understand the evolution of ice thickness. We force the system with temperature and precipitation, for example, and this usually comes from climate models, either global models, or usually we downscale this, or we use downscale data from regional models, and we have to constrain our simulations somehow with observational data. And so the first thing that is interesting is to understand if we can replicate the historically observed mass trends in Greenland. So until the 1990s, Greenland has been in relative balance with its forcing. The amount of mass gain by precipitation was balanced out by mass loss from runoff or calving. But we have observed since the 90s a mass loss trend, which is about in equal parts this due to increased surface melt, mostly during summer, and we also observe a retreat of outlet glaciers. So, okay, here we come finally to some of my own work. So I was in one of my projects looking at sea level contribution from the Greenland ice sheet until 2100. So how much sea level contribution can we expect within this century? And what we have done is, first we have initialized and run historical simulations with several different forcings to see if we can actually replicate the observed mass loss. And this is what you see in the first panel, or in the first figure on the top, where the gray shading denotes the envelope of observed mass loss. And we have been able to come up with an ensemble of simulations which fairly well reproduces this mass loss. And that means that we can actually use these simulations and we can rely on them much more with our projections. And then on the lower figure, you see an ensemble of projections, and these projections depend on different climate forcing that we used. So climate forcing from different climate models, or Earth system models, as we call them nowadays. And we have also used different emission scenarios. So exactly. So, and then what we came up with is that we will expect, depending on climate scenario and climate system or Earth system model used, we can expect something around 25 millimeters to 23 centimeters of sea level contribution from Greenland. And that might not seem that much, but you have to keep in mind this is only one contributor to sea level rise, and this number will likely be much more for places like Tuvalu. Okay, and then in a second project, I have looked at the more long-term evolution of Greenland. So we have we have just seen something on the scale of 100 years. Now we're looking at the multi-millennial scale. And this is work that I have recently submitted, and it's available as preprint on eGeosphere. So if you're interested, you can go check it out and leave some comments if you like. Okay, so what we see here on the left is simulation output over the course of 10,000 years simulated time. So we have looked at Greenland ice sheet evolution, and this is a simulation that has been forced by the Norwegian Earth system model output. So we have used this output. It's regionally downscaled, and then we have usually we don't have forcing available for 10,000 years, right? But we have used forcing that was available until 2100, and then we have schematically extended this forcing. And so here we use the climate or the emission scenario SSP5, which is a high emission scenario. And we have compared here on the top, you see a simulation where we have neglected the isostatic rebound. And on the bottom, we have actually included it. And what we can see here is that on these smaller timescales, so when we look up until 100 years, we can neglect this effect in our simulations. It doesn't make such a big difference because it needs some time to kick in. But here on this multi-millennial timescale, we see that it makes a huge difference. And the effect actually preserves much more ice after 10,000 years. But we do see that under this high emission scenario, we lose a substantial amount of the ice sheet mass. Now, this is only one climate model that we have used here. And then on the right side, you see a comparison of outcomes where we have used forcing from various climate models and different climate scenarios also. So it really depends a lot, not only on the scenario, but also on the climate model, how the future will play out. And in one case, the ice sheet is completely lost after already 4,000 years of simulation. And in when we compare this to outcome from other climate models, we retain large parts of the ice sheet. So we do really see here a big uncertainty lies in not only the climate or the climate pathway, the emission pathway that we will go, but also the Earth system models give very different outcomes. So there's high uncertainty in that. And that is why it's really important to sample a wide variety of this. Okay. This is already my last slide. Okay. I wanted to come back to the connection to Haifa basically here. So I have done a little bit of research on how sea level rise has been playing out in the Mediterranean Sea. And I have found that on average, since the 1990s, sea level has been rising around 12 centimeters around the Levantine coast. And so this is also in parts due to ice sheet mass loss. And on the top, you see here what the IPCC, so the Intergovernmental Panel on Climate Change, has projected until the end of the century for global sea level rise. And it lies somewhere between 0.5 meter and 1.5 meters, depending on which scenario. And because we are talking about these highly nonlinear systems, such as ice sheet and the climate system as a whole, how the future will play out is really a question of likelihood, and we can't really determine it ultimately. So it's important to keep in mind that ice sheets have a really long response time of thousands of years, and that means that decisions that we take today will have consequences in the long term. And this may affect millions of people who live in coastal areas. And yeah, I guess what is left for today is to think about how can we adjust to change that is already happening, and on which timescales do we plan. And for this, ice sheet model projections are really useful. Okay, thank you for your attention. Yeah, I'm open to questions. Happy to receive any.
Thank you very much, Charlotte. It was really indeed very enlightening for us, especially that we are very far away from any piece of ice.
Yeah. Yeah. Yeah, it seems very far. And then you understand, once you understand the connection, it's becoming very important for every part of the world.
So I opened the polling for questions from the audience. And since I don't see anybody altogether, so just opinion. Come on. So, or you were sleeping.
There's no stupid questions. You can ask really anything. I don't even know if I know all the answers, but certainly interesting to discuss a little bit.
I have a question until people are thinking on theirs. Did you explain, maybe I missed it out, about wet-based glaciers and dry-based glaciers?
You mean marine terminating versus land terminating glaciers, or?
Yeah, I mean, all the marine terminating glaciers, they are wet-based, considered wet-based, probably it, right?
You mean wet-based? You mean
As much as I remember when I studied geology, when I was living in Norway, you have two types of glaciers. Those that the base of the glacier is basically touching water.
Yeah, exactly. Yeah, that's exactly. So that's what we call marine terminating. So they are in contact with the ocean. Exactly. And so, of course, there's also land terminating glaciers, also in Greenland. But the difference is that once they are in touch with the ocean becomes an additional forcing factor. And warming of ocean waters contributes to marine terminating outlet glacier retreat. So the ocean temperature here plays a key factor. And it's really hard to include this in ice sheet models because usually we only model the ice sheet in isolation. And we somehow have to parameterize this effect of the ocean that comes in. And at the moment, as I showed you in this one slide, in the past decades, this mass loss from outlet glaciers has contributed to half of the total, or about half of the total mass loss from the whole entire Greenland ice sheet. So it is at the moment really an important factor.
Great. Somebody have a question? Yeah,
Yes,
Karen.
I do.
Or Sophie.
Yes, I would like to ask. Thank you for the lecture. It was really interesting. I wanted to ask, how do you calculate each factor? I mean, how much it will affect?
So it's not that straightforward. It's a very good question. So when I run ice sheet simulations, in its easiest form, I understand where is my ice sheet mass at the beginning of the simulation and where is it at the end, let's say after 100 years. And then I have the total mass loss. But that doesn't give me yet an answer about how much of this is due to surface processes and how much is due to outlet glacier retreat. And it's really, really hard to model this. I have done some simulations on this where, for example, I switch off the atmospheric forcing. That means I just keep that constant. And the only thing that I allow is for the ocean forcing to act on the outlet glaciers. And then I can take this output of a simulation and compare it to a simulation where I have allowed all the forcings to act. And then I see the difference. And I can do the same, for example, where I just keep all my outlet glaciers constant. I don't allow them to retreat. I just say that they stay in place, but I allow the atmospheric forcing to act on the ice sheet and surface mass balance to decrease and runoff to happen and melt. And then by comparing these simulations, I can get an idea of how the mass loss is portioned. But it's very uncertain, to be honest, because we parameterize a lot the outlet glacier retreat. It's really an ongoing study, or it's ongoing process to really include this ocean forcing in ice sheet models is really hard. So at the moment, the parameterizations we use are very, very crude, let's say, very basic, very schematic. So we get a rough estimate, but we can't really say that this is an exact number.
Okay, thank you.
You think there was another question?
Yes, Mike, sorry. My video is not working well, so I'm sorry I'm not seen. Do you have because you showed us in the last slide that there is an increase in sea levels, but I don't really see it in Israel. Maybe I'm mistaken, but do you see it in other places around the Mediterranean?
Okay, I actually don't know much about the Mediterranean, I have to be honest. I just did this little bit of research because I wanted to make the connection to you. But I guess what's important is that it's always a local process. What also happens is that you have local uplift, maybe due to tectonics, or, there's other processes involved. So I don't actually really know, but what effect it has currently on the coast of Israel, for example. I don't know if you are actually threatened by sea level rise at the moment or in the future, but I know that on average, the sea level in the Mediterranean is also rising.
All right, thank you. It's very interesting. I hope we're not that affected in the future.
Yeah, but in the long term, it's definitely something where you have to think about protection measures. I would assume.
Yeah, we do think about tsunamis sometimes. So yeah.
Okay. All right. That's a little bit of a different story. Tsunamis.
Yeah.
Related
Definitely.
that much to sea level rise, but yeah. So there might be stronger storm surges coming in, or yeah. If you think on the scale of millennia, then it will certainly make a difference. But I guess we as humans or as societies, we don't plan this far ahead.
All right, thank you, and a great talk. Thank you.
We do have influence clearly sea level rise because we do have major parts of our coastline with cliff, So Ionianite cliff. So with strong winter storm, basically they are falling, and with them the buildings that are broken. So yeah, and that basically cause of the sea level rise. That's the major.
Okay.
And the salination of the aquifer from the Bergen.
Yeah. Yeah.
Okay, so with no more questions, I thank you again, Charlotte.
Yeah.
Really thank you for everything. And we see everybody next week.
Thank you for having me. It was a pleasure.
Thank you very much.
Bye-bye.
Thank you.
Bye.